Well, welcome to our third talk on the seminar series. Professor Jack Sheen from mathematics is going to talk to us about finding low-dimensional representation multi-scale dynamics via deep adaptive basis learning. Is that mouthful?
Mouthful, yeah. Sorry, making too long.
Professor Sheen got his PhD from New York University, had postdoc appointments at Berkeley, Princeton, became a professor at University of Arizona, worked at University of Texas, Austin. He's been with us since 2005, I believe. Yes. And I've known him since then. He's been a pretty sophisticated computing user. Even in teaching, we set up a lab for him for teaching with what was about 20 Unix workstations, high-end graphics workstation. This is like 10 years ago, I think. And he's been using machine learning and exercising computing quite a bit with GPUs and high-end tools. So welcome, Professor Sheen.
Thank you for the nice introduction. And so I'd like to share with you my own experience in this area. Let's see. Oh, okay. So I think, okay, this slow. Here's the outline. So first I'll quickly describe my own journey from doing physical applied math to machine learning, and then integrating the two areas. And then I'll get to the specific problem of today, which is how to do a low-dimensional modeling for fluid dynamics. It's also known as the reduced order modeling. So then I'll point out the drawbacks from traditional approach, and then talk about the more recent deep learning framework. Then apply this framework to a specific problem just to verify that it actually works and delivers. So this is a physical problem of putting a Brownian particle inside a chaotic flow. And you can do that experiment, drop milk of droplets of milk into coffee and stir it, crazily stir it. That kind of experiment. And we're interested in a quantity called diffusivity. So if you wait long enough, there's a constant, a number coming out of all this, and that's what we're after. Then I'll show you some results of through deep neural networks and numerical experiments, and conclude from there. Okay. So first of all, I started out in the 1990s studying the traditional physical applied math, and so that is applied mathematical tools to solve problems arising in physics. For example, fluid dynamics, flames, light pulses. So depending on which quantity you look at, you could be looking at partial differential equations from classical mechanics, or Maxwell equation, and so on, right? Wave equations, all that stuff. Very interesting. And shortly before I joined UCI, I was at Texas. I started a project on the so-called cocktail party problem. So, when you go to a party, you talk to someone, and there are all these other people talking. But the human brain has this amazing capability to focus on the person in front of you, even though other guys are talking, but you can filter out all that. So there's a problem in electrical engineering, computer science, to design an algorithm to mimic the human brain. If you can recover that property, that would be fantastic. This turned out to be a challenging problem. I worked on it a couple of years, and also did some ear modeling to understand how the human auditory system works. And I would say the cocktail party problem is to hearing science what turbulence is to fluid mechanics. So I believe this will never be solved entirely, because it's a very difficult problem. So after a couple of years, I got enough of it, wrote a book, and then decided to do something else. Good thing is the mathematical tools are transportable. You can apply them to somewhere else. And I found out there's another application in chemistry, which is demix chemicals. And it's like the cocktail party problem, except it's not acoustics, but it's the chemical compounds and stuff. So I work with two faculty here in physical science, Ada Shaka and Phyllis in their labs in physical science. And that kept me busy for a couple of years. And then at the end of this period, deep learning started to make all kinds of noise. You went to a conference, you hear people talk about that, and I decided to have a try in it and see how it works in my own world. So I started deep learning about 2015, and starting from a problem of complexity reduction of deep neural networks. So these guys are usually very high dimensional. I had a collaborator from Qualcomm, and these guys are interested in putting the deep networks on phones. And phones have very limited capacity, computing power, memory. So you cannot just put all the deep neural networks on the phone. They're okay. They're big animals. They're okay for Google, Amazon, Facebook. They have tons of computing resources. That's fine. But for other smaller scale computing, you have to downsize them tremendously. So that's what got me into this area, is to figure out various ways to reduce the complexity of deep neural networks. And then more recently, I also got into recurrent neural networks, graph-based and so on, for epidemic modeling and forecasting. And this was before the coronavirus erupted. So a year before that, I realized, oh, this is a nice problem. But now there's more data coming out, hopefully, to study this area more in detail. Okay, so that's my own journey, how I ended up here. Now I'd like to switch gear to the problem I studied a little bit, to some extent, in the 1990s, fluid dynamics and a difficult problem called turbulence. And this is a few pictures of turbulence in nature. The wake of a ship, you often see this kind of a trailing vortices and lots of small eddies, right? So there are different sizes you see. There are big ones, small ones, and very small ones. So that's called a cascade. And similarly like this, a jet, you shoot it into the fluid, stir it, you can get something like this. And this is often what we see in Corona del Mar, probably. You look down the coast, you can see these sort of messy, chaotic flow patterns on the surface. So this is more or less a two-dimensional turbulent problem, because the turbulence is essentially at the top, okay, or the depth is not very much. And of course, you can get something like this in the middle of a windstorm. So it's more three-dimensional. Okay, so that's the problem. Now let's go to the, so that's good to look at, but what's the fundamental behind this? Well-known equations, Navier-Stokes, describe the motion of fluid. So this is the velocity. This is the pressure. This is the external force, for example, wind blowing. And in general, it's three-dimension. And we're interested in the case where the viscosity is very small, and that's typically the case for water in the ocean. Okay, and then of course to solve this, you have to prescribe suitable boundary condition. Okay, so here's one sort of simple way to define turbulence is a pattern of fluid motion with chaotic changes in velocity, energy cascade down to small scales, and small down to the scale essentially of that order. Okay, so a well-known physicist, Feynman, said turbulence is the most important unsolved problems in classical physics. And in mathematics, in 1934, Jean Leray constructed the weak solutions, global weak solutions, satisfying certain energy inequality. Till this day, mathematicians cannot construct a global smooth solution. If you can do that, that's $1 million delivered. Okay. All right. So this solution remained, something to work with, because it's mathematically established. And however, there's a lot of phenomena that you couldn't explain just by doing a weak solution. And so in 1941, Kolmogorov observed, he had a theory that observed the following. So if you look at the L2 norm squared, or the the sum of square of the gradient of the U, and you take certain ensemble average and multiply this by a small parameter nu in front, and this quantity in turbulence, fully divided turbulence, will go to a positive constant as the viscosity tends to 0. So this explains that this gradient U cannot be order 1. You know, if you cannot put in a smooth function, because if it's smooth enough, if the gradient has a uniform bound, this quantity will go to 0, right? But in this case, it's not going to 0. That means the gradient gets very, very big in turbulence. It's because of those small scales. Okay, so that's the Kolmogorov 41 theory. Till this day, there's no mathematical proof of this, though there were a lot of experiments that verify that Kolmogorov is correct. All right, and then talk about the two-dimensional turbulence. Krichin in 1967 developed a similar story for this, except he observed that in the 2D case, this quantity actually goes to 0. It's because the energy cascade from small to large overall. So you have smoothing, enough smoothing. So this is actually only true in 3 dimension, and the 2-dimensional turbulent theory applies to oceanography, for example, when the turbulence is essentially in the top layer of a fluid. Okay, so he was actually the last student of Albert Einstein. Okay, so now let's talk about the discretization of the equation. So there are several approaches to discretize the Navier-Stokes equation. The first one, all of these are using the idea of representation in terms of a basis function. So the classical orthogonal basis, the Fourier basis, is very elegant and analytical and so on. Of course, it's restricted to periodic boundary condition, and it's global and orthogonal. So, all right, and then there's in the engineering community, lots of people do finite elements. And the good thing is you can do physical boundary condition, more general domain, doesn't have to be periodic. It's local, but in general, non-orthogonal. So the bases have certain overlap. Dot product not equal to 0. And similarly, there were other bases in the 90s, very popular wavelets. And then other orthogonal polynomials like Chebyshev and so on. Okay, so no matter which one of these you choose, if you apply them to the Navier-Stokes, you encounter the following problem. If nu is very small, typically 10 to the minus 4, 10 to the minus 5 on that order, if you want to resolve these small guys, the small eddies, the cost is very high. So the fully resolved simulation is very extensive. You have to do it on the supercomputer and so on. Okay, so in particular, if you use the Fourier basis, you need the number of Fourier bases grow rapidly when the nu becomes small, on the order of nu to the minus 3 in 3 dimensions. So imagine that if you want to resolve, this cost will grow up quite fast. Okay, so a natural question would be, is there any way you can reduce this cost by constructing a small number of bases? It cannot be Fourier, but you look for other orthogonal bases that are more adaptive to the solution. So you know the solution has a certain pattern, for example. If you're allowed to observe and learn, right? So that's where learning comes in. If you're allowed to learn from your observations, can you do better? When Fourier constructed his basis, he didn't look at fluid, right? He was solving some other problem. He found the mathematical construction independent of anything. You know, you can apply it anywhere. But now we're solving a very specific problem. You have observations, either from the lab or from direct simulation. Can you observe and do something? So that's the new paradigm in this business. So now we're going to introduce the first work in this area, at least as far as fluid dynamics is concerned. In 1967, British man, Lumley, proposed the following idea. So he said, well, let's look at the solutions. He called it the snapshots of solutions. It's like you take pictures at a certain time from 0 to a certain time, t1, let's say.
you collect your samples, you observe, and you call it, if you put them all together, a certain value of viscosity, let's call it the training value of the viscosity, you have a data set, right? So, okay, so that's your observation. Now, he said, let's put these observation into columns of a matrix, and then you have a huge matrix. But this matrix turned out to be low rank. So if you perform singular value decomposition on the matrix, if you plot the singular value, you see that it decays quite rapidly. You know, like up to 100 or so, all the singular values decay, even though the nu can be very small, but the leading singular values, if you collect the hundreds, more or less, you cover them. The rest of them are very small. Okay, so that he said, well, let's take the first, let's say 50, 60 to 100 singular values, and the left singular vectors of this SVD will give you the orthogonal bases, right? They're by construction orthogonal, and they come from your observation. So if you, and then the physical information is encoded into the basis, unlike the Fourier basis. Okay, so then as soon as you construct your orthogonal basis, you just project the solution onto these bases instead of Fourier, and then you could have a numerical solution. So, okay, so that's this idea. And so usually it works quite well if you apply it at the same value of nu, right? So if your training and testing appears the same nu, it works very nice. So, however, in reality, we hope that this basis could be applied somewhere else too, right? That so to save your cost, because this value of nu is not cheap. You have to simulate. You have to do experiments. So, but you hope that what you have constructed here can generalize, can predict something else. So you want to apply it to another nu value, and hopefully the reduced commutation will give you a good solution. However, what often happens is if we reduce the value of nu, so if the nu test is less than nu train, then these bases will not be so good anymore. Because after all, what you observe is at one nu value. What you apply to is something different, right? So there's no guarantee that what you have learned would apply. In general, the solution can change when you change the nu, right? Okay, so that's the main drawback of this thing called POD. So after all, it's just linear algebra and doesn't reflect, I mean, it captures the physical solution at one value of viscosity, but that doesn't tell you how the solution transition when the viscosity values change. Okay, so this is where the framework of deep learning will come in. So I will propose the following. Instead of observing, collecting training data at one value, let's collect training data at two values. So here you take two sample values, call it nu1 and then nu2. And you do the same. You collect the snapshots and you have the observation. And now, instead of doing the single value decomposition, we're going to construct a nonlinear map to model the transition of physical solutions from the first viscosity value to the second viscosity value. And I'll show you the pictures, how they look like in a moment. So this is the nonlinear thing that's going to come in instead of just doing linear stuff. And what better nonlinear map can you do than the current deep neural networks, which is by mathematical theory can approximate anything. If you have enough training data, if you build it right, and then this nonlinear map will be a deep neural network. So in other words, here's where deep learning will come in to tell you how things change from nu1 to nu2. All right. So there you have some additional tool. So when you apply this to the, okay, so then the next step is you go to nu train, which could be just nu2 or a little bit less, it's okay. For simplicity, let's just take nu train equal to nu2. Does it go back? Okay. And then instead of taking the snapshots, doing the singular value decomposition directly at the samples and nu2, we're going to do it on the map snapshots in order to approximate the new test, right? The new test will be something sharper. I mean, it'll be something different. So when the new test in general is less than new train, so this mapping tells you what happens if new is reduced. So instead of doing the SVD at new train like POD, we're going to do it on the mapped snapshots. So that's the difference, because this will introduce additional physical effect. Okay, so that's more or less the general guideline. But you could say, well, this is easy to say, but can you show me one example how it works? So we're going to take some example and really do it. So there are a lot of physical problems to work with. The 3D wake flow, the picture I showed you behind the ship, that's a problem. And two-dimensional flow past the cylinder. So that's the two-dimensional adaptation of this 3D problem. And there are other problems in engineering, flow control. Okay, all of these problems are real-world problems, but a little bit difficult in the following sense, that not only velocity, but also you have to approximate the pressure. Okay, and pressure turned out to be a more difficult quantity to approximate. So there's that difficulty. On the other hand, pressure is something you want. For example, if you model the flow past the aircraft wing, you want the flow, yes, but in the end, you also want to calculate the lift and the drag, right? Because that's what these quantities are important for engineering. For calculating lift or drag, you then need the pressure. So there's complications in this problem. Okay, so in order to test the idea, I thought of trying another problem, more elegant in physics, and that's Brownian motion in chaotic flow. It's actually a very old problem, went back to Taylor in 1921, almost 100 years old problem, right? Next year will be a century. It's also known as the passive scalar problem. So here's how it's defined. So you put in a Brownian particle, and there is a constant in front called molecular diffusivity. Then here's the chaotic flow field you put in. And together, you want to solve this stochastic differential equation, or the Ito equation. And assuming you can get the solution one way or the other, and then you look at this quantity. So E is a unit direction. And you take your solution, so this is a vector, and you dot with the that direction. So you look at the displacement along the direction E, and square it, take the expectation and divide by T. And this quantity for a lot of space-time ordered or chaotic flows exists. In the limit T go to infinity, it converges to a constant. And this constant is called the large-scale diffusivity. Large scale meaning the T is large, space-time large. And so distance squared is proportional T and by this constant. Okay. And this constant is, however, very non-trivial. It's not something you can calculate by hand, except for very special cases. In general, we don't have a formula for it. Okay, so my goal today is to find a way to calculate the DE through deep learning and through POD, and then make a comparison. Okay, so of course you can do it directly, but in order to use a partial differential equation, I'm going to use the so-called Eulerian approach. So this is, if you follow the trajectory, that's called the Lagrangian approach. So I'm going to follow the Eulerian approach. So this is joint work with my colleague Yifeng Yu in math and our student Jianfeng Liu. Okay. So how do you do it through partial differential equation without doing Monte Carlo? So if you do it directly, you have to run lots of realizations and approximate the expectation divided by T. Okay, so look at this equation, a scalar equation, T sub T. The T is, capital T is temperature, for example, and V dot, switch gears, this capital D here is the gradient of D, and then D0 is the molecular diffusivity, Laplace in T. Okay, and in physics, it's also called the Fokker-Planck equation. All right, and then there's a so-called homogenization theory back to the 1970s. So I got into this business because one of the three guys, George Papanikolaou, was my thesis advisor, and now he's Stanford. When he was a postdoctoral fellow in Paris with Jacques Lyons in Collège de France. He worked with him and figured out the theory. And this is the result. The large-scale diffusivity, or sometimes also called effective diffusivity, is a tensor. It's defined like this. So D0, so delta Ij is the identity matrix. And then here's the average gradient of Wi dot with gradient Wj. Take the average, and that will define the effective diffusivity. And what is the Wi? It is a solution of this specific PDE. So here's W sub T. It's called a cell problem. So V is let's, for simplicity, take V to be space-time periodic, and you solve a forced advection diffusion equation. And you can show that this equation has a unique space-time periodic solution. When you put in space-time periodic velocity field, there is a unique space-time periodic solution up to a constant. So if you impose mean 0, there's only one solution to this. So suppose you solve this equation, you plug it in here, and here's the formula for DE. All right, so there's no stochasticity, everything deterministic. However, you have to solve this equation. And this equation is kind of like a linear version of Navier-Stokes, right? There's no pressure, however. That's good news. There's no pressure. You don't have to deal with it. However, there is a small parameter in front of the second derivative, just like the viscosity in the Navier-Stokes. And there is a forcing. So it's like a linearized force Navier-Stokes equation. Okay, so the same difficulty I mentioned before carries over to this equation. So the main thing is, how do you compute solution of this linear advection diffusion equation in the regime where D0 is small? And I'd also like to point out a connection of this formula with the Kolmogorov quantity called the energy dissipation. Remember, that's nu gradient U squared, right? So if I is equal to J, if you look at the diagonals, then this is exactly gradient of W squared. So gradient of W squared multiplied by D0. D0 here is just the nu, right? So if this quantity as nu go to 0 does not go to 0, that is like the Kolmogorov theory in this problem, right? So there's something remaining supported by the flow. Even though you send the molecular diffusivity to 0, the flow can sustain a large-scale diffusivity. So that's the so there's something Kolmogorov behind this formula. Okay, all right. So now let's look at some specific flows. The first one is the so-called Beltrami-Childress flow. So it's a two-dimensional steady Hamiltonian flow. I put this in there because for this case we know a lot about the DE. So if you take the Hamiltonian sin x times sin y, you generate a velocity from the Hamiltonian this way. You could check that the flow is very regular. So here's 0 to 2 pi, 0 to 2 pi, and there are 4 quarter cells in the big cell. And in each quarter cell, there is a spinning vortex going like this, and this is the other direction, and so on. So it's very regular. Imagine if you drop a particle in this flow, what happens? It's going to spin like here very regularly. If you happen to drop it on the edge, then you just move from here to here. These points at the intersections are saddle points, and over here in the center is a center point. Okay, so this is a regular case, and I'm also going to consider the time-dependent version of this. So it's given explicit like this. So cosine y, theta sine y, cosine t. So the main thing is there's a cosine t, and then here's cosine x, and so on. So this flow, if theta is equal to 0, it's very similar to this. But when theta increases from 0, let's say to 1, and becomes more and more chaotic. And therefore, let me show you a video of that flow. So right here. Okay. So this is when, all right. Okay. So I dropped 3 kinds of particles in 3 cells, 3 colors, and then if you wait in some time, you see the 3 colors start to mix, and So there are two invariant lines in the system, and the particles will not go across these 45-degree lines over here, but within the channel, the particles can mix. So that's the animation of this flow. So you can see that it's very different from the ordered flow where the particles stay in their cell. They don't go out to visit their friends in the other cell, right? It's like a prison. You just stay where you are. You cannot go. But in this case, it's like fully mixed. So that's the difference. Okay, so this is when theta equal to 1. If I take something smaller, let's say theta equal to 0.1, then you can make see a comparison. So okay, so here it is. So there are 3 colors. There's some mixing, so you see there's some leaking going out. But the core of these particles, the green guys will stay here green, the red is here, and the blue is here. So there's some exchange of mass across cells, but majority of the particles stay where they are in the same cell. This is when theta is small, so it's very close to the ordered case. But when theta equal to 1, that's the first demo you have seen. Okay, so just to show. Okay. All right, back to.
Are they all converged calculations?
Yeah. Right. Okay, and then, so this is the main thing I would like. And generator working together and adversarial network. So here's the input, and here's the output, the fake picture, right? So here comes the result. And this guy is supposed to be carry a lot of fine structures, and you see, indeed, you get some of the fine, structures in there. And this one here is mapped to this one. Overall, they look similar, but there's a lot of fine detail that has been created because of the learning. He has seen those pictures at 10 to the minus 4, but unfortunately, you cannot create. We try very hard. I thought we could almost create the fake pictures like the computer science people show, but somehow we couldn't get it to, like 10 to those pictures that show you 10 to the minus 4. But we get something kind of, at least has some small scale structures. On the other hand, in this problem, we're lucky because we're after the basis function. You don't have to find the solution. You just find the basis function with similar regularity as the solution. That's good enough. Okay, so that's the output. Then let me show you some result just to compare. So the training is at 10 to the minus 3. The standard training, 10 to the minus 3. And if you do the POD, you just do single value decomposition there. And then you get the result here. Okay. And the fully resolved result, just a ground truth to compare with, is over here. So we train here, we're going to apply them to smaller D0 values, 4, 5, 3, 2, and 10 to the minus 4, right? Smaller values. So and then for the deep network, we also collect observation at 10 to the minus 2. Remember, we need 2 observations, and then construct the mapping and learning over here, from here to here. And then you can compare the results. It's easier to look at the relative error of these two methods. So as you see, as D0 gets smaller, the SVD, the standard POD, the errors increase as they usually are expected to do as D0. So they make errors, but look at this SR gun, the errors actually go down amazingly. And that's because we modeled the sharpening of the structures. So this, I think, is something. The deep networks taking more observation, they can do a better job. Yes, sir.
And so for each training, so you have like mapping the relationship between like the two features, like two scales, right?
Yeah.
So you actually do several times to mapping all these, because in the table there are like five different D0 values.
Oh, right. So actually, we just because when we train the mapping here, we just applied once. So we didn't apply, for example, 2 times, 3 times, 4 times. That
just one.
We just apply once.
Oh.
We could have applied twice if it doesn't work. So far, we just try applying it once, see what happens.
Oh.
In this case, you already see something. You asked a good question, so let's go to the next one. So in this case, we train the network from 5 10 to the minus 3 to 10 to the minus 3, a smaller value D0, and test them at 10 to the minus 4. So there are 3. And a similar trend appears. So in this case, we test a little bit less. So again, you see that the improvement is dramatic in this case. Okay, so this is, I think, the amount of sharpening that we learned in the deep networks happen to match, I think, what is going on in the test. But values of D0. All right, the last one I'll show you is this. So we train the networks from 10 to the minus 3 to 10 to the minus 4, and then apply them to 2 times 10 to the minus 5, 10 to the minus 5. So here it is, very nice, 5.9% to 1.1. But when you apply the 10 to the minus 5, the improvement is just 1%. I think in this case, if we have done what you said, apply it twice, maybe you'll do a lot better. Because that just means you sharpen it once by deep networks. It's probably not enough yet to mimic the true solution at 10 to the minus 5. Maybe I'll apply it one more time. Yeah, so that could happen.
Okay, so for example, so you are doing D02 over D0 minus 10, so you are still taking the same value, the same ratio?
Yeah,
but different value.
different value. Okay, so that's the sort of conclusion. Is I showed you a deep learning framework to improve the classical, the good old POD, and improve the prediction. And however, there's a lot of, to be understood. For example, how to select the two values optimally to learn the nonlinear mapping. And the other one is, so far the deep neural networks is trying to mimic what is happening in the solution to the PDEs. There's no analytical or mathematical connection between the two. Can one establish something more rigorously or extract certain properties of the networks mathematically so that it mimics better the PDE? Then they'll be even more powerful. And this part hasn't been done yet. On the more computational side, the three-dimensional problem hasn't been solved. Part of the reason is, of course, more expensive to simulate the PDE. And then also, the three-dimensional super resolution deep neural networks haven't been constructed satisfactorily yet. So the convolution is a big step in deep networks to do filtering. Convolution is very easy to do in 2D, but in 3D, there's a lot more work to do a good job on convolution. Anyway, I think there's a lot to be explored in 3 dimensions to continue this line of work. And also eventually want to get back to the physical problems or other problems people have in this area, where you want to do reduced order modeling of a complex problem. In addition to just do single value decomposition, can you use the deep learning to get more out of it? Okay, so that's all. Thank you very much. Here, the good old Lumley is 67, and then the our two papers. First, we did just a straightforward POV, actually, just to learn the stuff, and then this is the more recent one. And this is the deep networks that we took over and make some adaptations. Yeah.
But these slides, as well as the talk, will be posted online, as we've been doing with the other talks. We have some time for some questions, if you wish.
The measure of the error, right? This is one number.
One number, yeah.
That was the number you wanted to predict. I mean, can you look at, can you extract other attributes of simulated images and see other things are coming out well or badly? Or...
Yeah, so thank you for the good question. In general, if this number comes close, and then the derivative information has been approximated quite well. So that's...
What do you mean by...
So in other words...
Like how you quantify...
Right, so the relative error of the gradient of solution with the... so what you find from the low-dimensional solution would match the high-resolution solution up to a small relative error in L2 and also in H1. Yeah. And in H1. Right. Yeah.
So that one number is approximate.
Approximate, right. Mm-hmm. Yes.
For your loss function,
yeah.
that's how you scale to them.
Oh, that's
the scale.
Yeah, those are just you play with them empirically. Of course, we have some guidance from computer vision, because these guys, when they produce these fake pictures, they already play with these numbers. So what we just do is, start from there. Yeah. So this is more or less trying to utilize the current tool in computer vision to physical science problem. Well, in 2 dimensions, thank God, the physical solutions look like pictures. So you apply them directly. Yeah.
On the next slide,
yeah.
There are 2 color scales. Which cannot match on top and bottom.
Which one?
Here.
Here.
Yeah.
Okay.
The scales are different on top and bottom. The color scale.
Oh, okay. The colors. Oh, sorry. Yeah, sure. I guess he used a low color maybe to produce something little bit show you give it more contrast or something. Yeah, thank you for pointing that out. But more or less the structure is there. Yeah.
I mean, if you scale, if you have the same color, do you see the same structure?
Yeah. I mean, the fine structures are still there. Yeah. Yes.
How many pictures are there in the training set?
About 1,000.
1,000.
Yeah.
So
from 0 to 2 pi. So you collect. Yeah.
So compare with, I mean, for this type of question, I think you can also do it with CNN, right?
With CN?
Yeah.
It is a CN.
It is CNN, but it's a GAN network. So what's like the benefit of using this specific kind of? Did you compare it with like other?
Oh yeah, right. So this is the super resolution GAN. The main thing is to increase resolution as much as possible. So that's what we went there for, right? And there are other GANs. There are other GANs. First of all, for example, SR-ResNet. That's another one. This one will give you a little bit more signal-to-noise ratio enhancement. But if you look at the naturalness of the enhancement, the BGG does a better job. So that's why we select this one. Yes.
So actually, the 1,000 images, actually the number is a little bit small, I think. But so
yeah.
you can, so this network can use like a small set of like images to produce good result, right?
Yeah, for the fake pictures in computer vision, I think they have more data. Yeah, to do it. This may be part of the reason why we cannot get the good looking pictures like they do. I mean, they have a lot more. But our data are just computed by my students. So, so 1,000 I think is already quite a bit of data. Yes.
1,000 images.
Yes.
I mean, presumably, are they in sequence?
In sequence in time. Yeah.
Yes, it needs to have in sequence.
Yeah.
Then, I mean, you train at 2 different values of viscosity.
Viscosity.
Right?
Yeah.
But if some sort of time scale was changing the viscosity, then you are presumably doing the exact same time slice.
Right.
Viscosity.
Mm-hmm.
But if the time scale is changing, just like the length scale,
right,
then
you might miss something.
Yeah, like or you try to account for that, or you look to see.
Yeah, so we're fortunate in this case because the solution is time periodic. So we just go from 0 to 2 pi. That's good enough.
But just because it's time periodic doesn't mean that smaller time scale, right?
Right.
Just like eddies are appearing in space and changing.
Well, we're changing in time. Yeah, so you're right. Yeah. So that could be another source of
making it more difficult.
More difficult, probably. Yeah. Sure. That would be, yeah.
Can you do any data augmentation on these 1,000 images?
Data augmentation. We could. So how do you, for example, adding rotation and stuff like that?
Yeah, with satellite images, they can, turn
right.
60s.
Could be, yeah.
Objects you cannot obviously put upside down.
Sure, that's a good idea. Yeah. Yes.
Like this part of the world, like how do we increase the accuracy?
So here we limit our reduced basis to 100. So we just use 100 basis for all the cases. I think if you put in a little more basis function, that's one way to improve a little bit. The other one would be to, like you said, improve the data quality. So, put more than 1,000 images by collecting snapshots in time, maybe not uniformly, but randomly, for example. You may hit those structures better. So we haven't tried that. Our collection is uniform in time. And we didn't do the data augmentation. So it's possible if you put in more data that usually the deep networks can do better job if you feed them more. Yeah, big elephants eat a lot. But we just can't afford to feed this guy. We only have one computer and one student, so 1,000 is what he manages to. Anyway, it's a good start, but there's so much more to it. Yeah.
You could ask the question, if you interpolate, since the data are solutions
Mm-hmm.
equations,
Yes.
and you interpolate between two snapshots using, a few neighbors in time,
Yeah. Right.
do some sort of reasonable interpolation,
Mhm.
guess it,
Right.
and then of course it wouldn't be quite right.
Yeah.
But then feed it into the network
Mm-hmm.
and see if it sort of somehow
Yeah.
improves things.
Improves
and then it's costing nothing, right?
Yeah. Yeah. Right. Good idea. Mm-hmm.
That's a different kind of data.
Right. Although when you do that, you leave the domain of the solutions.
Absolutely.
Right.
So the mathematician says you better not do that, right? But you're gonna have to try it.
Try it. Yeah.
And
See if. Yeah. Exactly. Right.
you haven't left it very far.
Any more questions? Before I let you go, just quick, we're not gonna have the social hour this Friday. And if you're interested in more up to the minute info, we have a Twitter feed that you might wanna join. It's off of our web page, you can find there, the SML. Thanks again, Professor Jack Schmidt. The next talk will be in a couple of weeks from the Department of Physics. Thank you.